Okay, so let's get started. So we saw in the example how we got the transfer functions. Let's cover the general case now. So the general result of step 3 is that we obtain the linear state space model we know how to get to this point. So let's see how we go from this point to the transfer function. So step 4 is L and then the plus transform with implied assumption. Okay. So we're going to use the dictionary. First of all, okay, let's call this star A, star B. So that's Laplace transform star A. Left-hand side, I have x prime dot vector. Or I should say something that Laplace transform of a vector is the vector of the Laplace transform of every component. Okay? And everything holds for vectors going to each component. So the Laplace transform of a vector of derivatives is the vector of the Laplace transform of every derivative. Clear? So, what do we have for the time derivative of the vector x prime?
Thing you circled,
I
square.
think that I have squared, exactly. So the Laplace transform of the vector x prime dot is going to be s. Same thing as vectors. We could have put this in dictionary. You can put here vector with vector with vector. Okay? So S, and now I'm putting bar, bar. The underneath bar means vector. The over bar means Laplace transform. Minus that's what the left-hand side gives me. Equals a constant, A is just numbers, right? A constant matrix factors out, like in the scalar case, a constant factors out. I'll be happy to show you outside class if anybody, a quick proof of that. It's pretty trivial algebra, but I'm trying to minimize proofs, so. Okay, but like in the scalar case, a constant factors out. In the vector case, a constant matrix factors out. So that's going to be A times the Laplace transform of x prime, which is x prime. What about the next term? Vector B times u prime. Who will tell me what that's going to be equal? Someone help me?
B,
Okay, one.
bar underneath,
Okay. B vector.
times x, bar on top and bottom. Never mind.
What is that? B factors out.
Okay, u bar top and bottom.
Is that a vector?
Alright, just put it on the top.
Exactly. And u prime on the top. Good. Okay. Someone else. Someone hasn't volunteered. Megan, you look like you're ready.
It's just gamma, D, bar on top and bottom prime.
Excellent. Exactly. Exactly. All right. What's that now? What am I going to do with x prime of 0?
Okay, you move A to the left side.
No, what am I going to do first of all? Okay, I'll ask you that one afterwards.
Move to the
But
right side.
whatever. I'll ask another one, so last one. Give me the next step. What do I do with x prime of 0?
You say that that was 0.
Exactly, the implied assumption. Okay. So, one, what you're trying to tell me is next. What do I do?
You do A to the left side.
I move this to the left side.
Mhm.
And so I have S x prime bar minus A x prime bar equals B U prime bar plus gamma D prime bar bar, right? And I want to be able to solve for x prime bar. Can I just factor x prime bar and write S minus A times x prime bar?
No.
You divide
No.
by A.
What do I have to do?
You divide by A.
Who said back that identity? Someone said identity? Okay, Alden? I cannot factor x prime bar like that because S is a scalar, A is an n by n matrix. You cannot write S minus A, you cannot have S minus A11, A12, A21, A22. That's impossible. You cannot have scalar minus a matrix. So there's a trick that we have learned also in COT, and the trick is you can rewrite Sx prime bar as S identity x prime bar. The identity matrix has the property that identity times any vector is equal to that vector, so you can produce an identity before x prime bar. Okay? So now I have S times identity minus A. That I can do now because identity and A have the same size. S identity is a base of the same size as A. Yes.
What does I look like? I know it's like with 1 and zeros, but I don't remember. Okay, got it.
Okay. That's the identity matrix. So that times x prime bar bar equals B U prime bar plus gamma D prime bar bar. Well, my unknown is x prime bar bar, right? Before I was solving for x1 prime bar, now I'm solving for x prime bar bar. What's that? That's simply the system AX equals B that we dealt with in COT. What's the solution of AX equals B? Parenthesis here, I don't want to confuse this X. I don't want to confuse this X with this X, okay? This is the X prime bar bar. Remember in COT, what's the solution of this? A inverse times B, exactly. So to solve this, you multiply both sides of this equation, and important here, we're talking about matrices and vectors. Order is critical. If you mix up the order that you write things in multiplying matrices, that's not a little algebra mistake. That's a significant conceptual mistake because you're writing impossible operations or totally wrong operations. So that's significant loss of grade. So be very careful to have the order of things correctly. And you ask me what S is. S is anything we want it to be. So as long as there is a single value of S for which an inverse exists, we can do it. And there will always be a value of S for which an inverse of Si minus A exists. The reason is, if you take S very, very large, okay, you take S very, very large, then what is Si minus A? It's like Si, right? and Si is a matrix that has an inverse. So always Si minus A, always there exist values of S for which Si minus A has an inverse. So we can multiply both sides of this equation on the left, careful, the order is very important, by Si minus A. So if we do that, all right, all the steps, Si minus A inverse times Si minus A x prime bar bar equals Si minus A inverse times B times U prime bar plus Si minus A inverse times gamma B prime bar. Just right. That's something we don't confuse us. What's inverse of a matrix times a matrix? Any matrix?
1.
Not 1.
0.
It's not 1. It's
The matrix itself.
inverse of a matrix times a matrix. Identity. An identity times anything is anything. So from here follows that x prime bar bar equals Si minus A inverse B U prime bar plus Si minus A inverse gamma B prime bar. Okay, at this point I'm going to get introduced something that's just algebra, where you have the product of a matrix times a vector. If you have, so here's an aside. A matrix times a vector. First of all, to be able to multiply, if this is n by 1, this would have to be, let's say, m by n. So that would be something like m11. Well, let me take. So this matrix has to have n columns. To be able to multiply with the vector n by 1, this matrix has to have n columns. Let's write the column vectors as m1, m2, mn. So I have that times the vector v, and let's write the components of v as v1, v2, vn. You can show that you can rewrite this product as the sum m1 vector times v1 plus n2 vector v2 plus mn vector vn. So that means I have the gamma d prime bar. The gamma d prime bar can be rewritten if I call lowercase gamma with underline the columns of the matrix gamma. And I have R disturbances. And here the Laplace transform, here is my d prime bar bar, which is components d1 prime bar, d2 prime bar, d prime r bar. That is equal to a very quick numerical example. What I'm saying is that, let's say I have 1, 2, 3, 4 times d1 prime bar, d2 prime bar. Okay? What? What's the result of this? Well, we should be able to multiply. This will give me 2 by 2 times 2 by 1. The result will be 2 by 1. So the first component is going to be this with this. Matrix vector multiplication, d1 prime bar plus 2d2 prime bar. And the bottom component would be 3d1 prime bar plus 4d2 prime. So that's this product. And I'm saying this is the same as taking the first column, 1, 3, times d1 prime bar, plus the second column, 2, 4, times d2 prime. What's the result of this?
Same.
Scalar multiplying this makes it d1 prime bar, 3d1 prime bar, 2d2 prime bar, 4d2 prime bar, right? So that's d1 prime bar, 3d1 prime bar, plus 2d2 prime bar, 4d2 prime bar. Add them up. What do you get? Okay? Add.
Those gammas have the vector notation under them?
Yes, because they're column vectors. So if this was the gamma matrix, okay, this would be.
So yeah, so in that addition line, you should have the
Oh yes, thank you. Yes, please put the underlines here. That's why you get the Okay. So all I'm saying is, in x prime bar, I can rewrite my gamma d prime bar as the sum of gamma I di prime bar. So this was a parenthesis, this is an aside. Getting your note, but I'm going to erase that. Because so this is an aside, making that point. Just.
What are the dashed lines in between the variables?
It makes a partition matrix. You just simply clearly delineate that this is first column, second column. It's just a way of note the different column vectors of the matrix. You typically use partition. So, okay, if I hide this, going once, going twice. So that means that, continuing from here, x prime bar bar is equal si minus a inverse b u prime bar, and we can rewrite that plus si minus a inverse sum of gamma I di prime bar. So gamma d prime bar can be rewritten in this. And I can put this inside the sum. Okay? I can move the sum outside. So the final thing I want from here is that x prime bar bar is equal si minus a inverse b u prime bar plus the sum over all disturbances of si minus a inverse b, gamma I di prime bar. So that's the Laplace transform of star A. Let's call this double star A. Okay. Very much like we did in the example. What did we do? We Laplace transform the equation and solve for x prime bar. That's all we did. And that's the solution for x prime bar. And we use the implied assumption. So that's why we don't have x prime or 0. Okay, everyone?